Hi guys, long time no see. So today I will present about segment tree. It's a data structure and it's like you have to build a data structure and it's not built in library, and segment tree used to solve a range query problem. Range query problem. Range query problem. For example, giving an array, and you have a query asking for L to R, and it must return the value of minimum or maximum or sum of the interval a L to R. It asks for the value of interval on minimum, maximum, and sum. And so the naive approach, for example, like you're given queries. So the complexity of the algorithm will be O of query times, and it's extremely large to solve. And so we introduce to segment tree. It will solve range query problems in complexity of O or query times logarithm of n. It's pretty fast. It's faster than the naive approach. So we'll show you the I'll show you the structure of the segment tree. So given an array of n, for example, like 7 elements, you build a segment tree. You build a segment tree. The structure, the segment tree consists of nodes. And each node represents the interval of the array. So nodes, for example, we have 7 elements from 1 to 7. So we'll build a segment tree. This is the root. This is a root of a segment tree, and it will hold the value of interval from 1 to 7. And then this is a parent node or root node. So segment tree is kind of binary tree. So on the left side, it has two children. On the left side, it will be it will hold the value of 1 to 4, and the right side will be 5 to 7. And this will be 5 to 6 and 7 to 7, and this will be 5 to 5, and this will be 6 to 6, and 1 4 plus. It will be 1 to 2 and 3 to 4. This will hold the value of 1 to 1 and 2 to 2, 3 to 3, and 4 to 4. This a basic form of the segment tree. Each node holds the value of the interval from L to R, L to R, yeah. And for example, like we have an array of 7 elements from like 1, 2, 0, 9, 0, 0, 2, yeah, 7 elements. So yeah, 7 elements, because this one hold, we will build a segment tree hold the sum of the interval. So this nodes hold the value of sum of interval 1 to 1, 1, 2, 3, 4, 5, 6, 7. Okay, so okay, so the value of this node will be 1, 2, 0, this is 4, so 9, this is 5, so 0, 0, and 2. Yeah, and so this node holds the value of 1 to 2. So 1 to 2, you take the left node side and you plus the right side. It will become 3, and this node hold the value of 3 to 4. So 0, 9, 0, 9. Okay, it will be 9. And 5 to 6, 5 to 6, and you take the left nodes, you plus the right nodes, the value of right nodes, so it will become 0. And 7, it will, yeah, it remains 2. So plus 0 plus 2 is 2, 3 plus 9 is 12. Yeah, 12 plus 2 is 14. Yeah. 14. So whether you ask the query, when you ask the query from left to right, for example, like I want to know the sum, yeah, the sum of the interval from 3 to 6. So I ask the query from 3 to 6. Yeah, okay. First one, 3 to 6, and yeah, you pass from the root of the tree. So it here from here 3 to 6, right? 3 to 6, right? But this node holds the interval of from 1 to 7. So you have to split them. Yeah, you have to split them so it will move down here, and then yeah, it will be moved down here because yeah, 3 is inside the interval of 1 to 4, and 6 is inside the interval of 5 to 7. So yeah, we'll transverse into the leaf of the tree, and then return the value and plus them and get the last value, like 3 to 6. So here is 1 to 4, and you move down here. Down here it holds the value of 1 to 2, so it's outside the range. So you move to the right side, because it holds, yeah, 3 to 4, 3 to 4. Yeah, it yeah, 3 to 6. So you return the value. It will be 9. Yeah, return the value, and the left hand side will be 9. And then you move to the right side. The right side 5 to 7, 5 to 7, 5 to 7. Yeah. And then you check the right side. The right side 7 to 7 is outside of the 3 to 6, and yeah, you have to move to the left side. So 5 to 6, yes, it's inside the 3 to 6. So you return a value, and here, and at this node the value is 0. yeah, the value is 0, so you return it, and you return the 0 to this node, and you return the 0, and 9 plus 0 is 9. So the query will be 9, yeah, 3 to 6, it's 9, yeah. So here you see that we only traverse the branch of the tree, but we can see that from each level of the tree decreased by 2 times. It decreased by 2 times. Yeah. From here it holds 7 elements, but at this node it holds only 4, and this only, and it holds only 3 elements. So it decreased 2 times. So the height of the tree will be log of n, log of n, log of n. Yeah, so the tree will be log of n, because we only traverse the branch of the tree. Yeah, at each level we only traverse the nodes 1 time. You can see here, yeah, only traverse the nodes 1 time. So the complexity will be log n per query. So at q queries it will be q times log n. Yeah, the complexities will be q times log n. Okay, it's a basic idea of segment tree. So yeah, and yeah, it's segment tree. And if it asks for a minimum query, yeah, okay, if the problem asks for the minimum or maximum query, you do like sum instead of plus two elements. You get the minimum and maximum between 2 values, and then return it to the the parents of the nodes. Okay, and so yeah, it's a basic idea of segment tree. Yeah. Okay. Yeah. So segment tree, basically the idea of segment tree is pre-compute the value, and when the program asks for the value, it will return the value, yeah, easily, instead of recomputing the value that's already computed. Yeah. Okay, so yeah, that's the basic idea of segment tree. So here but yeah, that's not the strongest part of segment tree. Yeah, so if we already built a segment tree, like yeah, 1 2 4, yeah, 1 2 2, and 3 to 4, 1 2 1 2 3 4, yeah. So except for we have an array of 4 elements, like 1 2 0 9, yeah. So 1 2 0 9. Okay. So we build the maximum segment tree. So it will return the max is 2, return the max 9, return the max 9. Okay. So yeah, we have a segment tree. Yeah. 1 2 3 4. Yeah. 1 2 4. Yeah. So if if you modify an element, like you change this one to 8 with another, if this was another data structure, the program, you have to recompute, you have to rebuild the data structure, but with segment tree you don't need to do that. And the complexity to build a segment tree is O of n. If you modify a value, and it will cost O of n complexity. So that's a naive approach. So we'll optimize it to O of log n. So if the first value was 9. So if I call a function of set I x, it will set the ith element to x. Like I call set for 8, okay, set for 8, so this element will become 8. So set for, okay, set for, okay, if I want to modify the fourth element, so I will traverse the tree like I did before. So fourth element, we consider left side. So 4 is out of bound of this left node. So we move to the right node. We move to the right node, and so here we it's split into 2 nodes, and then we want to modify the fourth value, but the left hand side is already 3, so it's out of bound of 4. So here you move to here, and then you modify the 8. You modify the value to 8. You modify the value to 8, and then you went upward. It comes backtracking. It's called backtrack, and then you backtrack. You get the maximum of these 2 nodes. It will become 8, and then you backtrack to this node, and it will become 8. So we only, instead of rebuild the tree with O of n, we traverse the branch of the tree, and we get a complexity of O log n. Okay. So this is another basic operation on segment tree. So we'll move to the next. The next operation is we have query and we have set. So, and then another one, we have the we have set on ith element. So what if we modify the value on interval? What if we modify the value on interval? So the naive approach is you iterate over from L to R, and then you set the ith value. So the complexity of this operation will be n log n. N log n, and it weighs too expensive. Instead of you can rebuild the tree. So we'll optimize this function to O log n. Okay. So next, we'll modify the value. Like for instance, like we have 4 elements, 1, 2, 0, 9. We want to modify the value on 1, 2, 3, 4. We want to modify 2 4 5, yeah, 2 4 5. We have two ways to modify. The first way is to assignment, and the second one is add, we assign the values from in the interval from 2 to 4. We assign it to 5, so it will become 1 5 5 5. If we modify the value from 2 to 4, we add 5, so the result will be, this is 1, this was 2, so 7 2 0, so it's will 5 9 13. Yeah, we have two ways to modify the value, but this time I'll only talk about adding value. The assignment value, by adding value, the assignment function is easy, and you can do it at home. So yeah, we'll only talk about adding. Yeah, so we modify on interval, modify the segment tree on interval. Yeah, this is the strong data structure. It is the strong data structure segment tree for solving the range query problem. Besides segment tree, we have a lot of data structure like sparse table, and for building this sparse table, you text it cost and log n and query in O of 1. Okay, it's pretty fast. In segment tree, we build in O n and we query in O log n. And besides, we have Fenwick tree. It's a binary index tree, abbreviated as BIT. But in my opinion, we should these two tree has the same function. So I prefer using segment tree over Fenwick tree. For coding part, this tree is easier to code than segment tree. But in Fenwick tree we have hidden constants, and we can easily make unavoidable mistakes, and it will spoil our program. So back to the modify part. Modify part. So as we know, at first our nodes contains only the value, and and the left and right, representation. So at this point, our nodes only contain this, and the pointer to the left and the pointer to the right. So at here we'll add one parameter to it, and we name it lazy, because this technique calls lazy propagation. It spread lazily. So I'll demonstrate the idea, and you see. For example, we have a segment tree with 5 nodes. Node 5. The array of 5 elements. So 1 to 5. 2 2, 3 3, 4 4, 5 5, 1 1, 2 2. There are many ways to represent segment tree. Yeah, the common way is to use binary heap. You can search it on Google. Binary heap. Yeah, it basically the array of with consider index I. So the left child will be 2 times I plus 1, and the right child will be 2 times I plus 2. Yeah, it's ways to represent the array, the tree. So I don't talk about it very much. Yeah. So 5 elements. So yeah. Okay. We'll name we'll create the array of the value 1 0 0 3 2 1 2 3 4 5. Okay. Okay, so the value will be here, 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 here. Yeah. We'll build the maximum, the minimum. No, I'll build the sum. Yeah, sum. Sum segment tree. So this will be 1 1 3 2 5 6. Yeah, 6. So if we want to modify, if I call the modify function with from range 3 to make larger range 2 to 4. Yeah. Okay, 2 to 4. Okay, 2 to 4, and I call the add function. I will add 6 to each element from 2 to 4. So at 6 it will become 6 6 9 2 1. Yeah, kind of. Okay, so at first we'll traverse the tree starting from the root node. So yeah, we take 2 to 4, the interval from 2 to 4. So 2 to 4, and it consists of both sides of the tree. So we go deep in both sides. Okay, we go deep in both sides. Okay, and deep in both sides. Okay, and then at this point 2 to 4, 1 to 2. Okay, both sides, and 2 to 4, 1 to 3. So we go deep in both sides again. Yeah, we go deep in both sides again. Go deep in both sides again. And at this point, because this is a leaf node, so we'll add 6 into its lazy parameter, lazy variables. Sorry, lazy variables. But this is already a leaf nodes, so yeah, it will be 6. It will become 6. Lazy add to the value, it will be 6. Oh, 5. Oh, 6. Yeah. And then you move to the right side, because 2, this one contains 2, so it will be 6. It also the leaf nodes. Yeah. Oh, and then you backtrack the value so it will become 7, and this will become 13. And yeah, you move down the side for 3, you add 6, but 4 to 5, yeah, it's already in that. Move to the left side and add 6, it will become 9, and you backtrack the value, and it will be 11, and plus, so it will be 24, yeah. So yeah, I accidentally set the modify really special, so I will reset the modify. I will set the modify from, yeah, from 1 to 3, yeah, from 1 to 3, and I will add 6, yeah. 1 to 3, yeah, I'll add 6. Okay. 6, yeah. Okay. 3, 2. Okay. So yeah, we're starting from the root node, and you see on the right side is, yeah, it out of mod from the interval of 1 to 3. So we transverse into the, yeah, to the left side. But at here, yeah, you can see that the 1 and 3, yeah, the interval of 1 and 3 is already set. So it's already inside the, yeah, it's already inside the, yeah, already inside the interval. So at here, we'll set the lazy of these nodes, to 6, and then yeah, add the lazy to the 6, and then you push the value, because this holds the from the interval of 1 to 3, so it will have 3 elements. So the value it holds will be, yeah, from the first one it holds 1, okay, it holds 1s, but after, yeah, after pushing, and yeah, it will become 19, because 1 plus 6 times 3 is 19. But yeah, you don't have to push down all the value and then you return the value. Yeah, you backtrack the value, yeah, 5, so it will be 24. So at this point the lazy value is 6. So whenever you try to reach the node, or whenever you try to query the node, you try to push, you push the lazy value to the both sides of the nodes, so that you can get a correct value. So yeah, I modify, and if I query from 1 to 5, I still get the 24. Yeah, it's true. Yeah, 6, 6, 9, 2, 1. It's 24. Yeah. Okay, it's 24, right? Okay, but yeah, at here, we don't have to modify this value yet. And then whenever and if I try to query 1, 2, I transverse to the nodes, and then before visiting the nodes, we push the lazy value to each cycle nodes. So the lazy will be 0, and you push it 2, so the lazy values will be 6 and 6, because this segment holds 2 values. So when you call the query, or when you visit the query, or when you visit the nodes, you push the lazy value to the actual values of the nodes. So it will be 6 times 2 and plus 1, it will become 13. Yeah, and then because this holds only one value, is 3, so with 6 times 1 plus 0, so it becomes 6, and then 13 and 6, yeah, it's 19, it's correct. And you push the value to leaf nodes, yeah, you push the value to leaf nodes, and then but yeah, wait, actually lazy is still 6 at this point. So whenever you try to like query 1 1 or query 2 2, the nodes, the parent nodes will push the lazy value to the lazy value of the leaf nodes, and whenever it push, and after it push, and the lazy value will be pushed inside the actual value, and because of it, this leaf nodes holds only one element, so it will be 6 times 1 plus 0, so this nodes will become 6, and lazy is set to 0, and yeah, and here example like 7, yeah, so actually you don't have to backtrack because you already backtrack the value, yeah, on the on the parent nodes. So that's how you querying. So it's, you can see that it propagates slowly, lazily. Yeah, we don't have to traverse to the nodes that is unnecessary, but yeah, we only get the true value of the nodes, and whenever we want to get more specific value, we at that point we'll push the nodes and get the correct value. All operation will work in all log of n because we only traverse the branch of the tree. Yeah, that's all. That's segment tree, and yeah, hope you like it. Thanks.